wonderful TAs this semester, and one of the ways in which they've been wonderful is by catching my sometimes mistakes, sometimes omissions. So Yoon has pointed out to me that I failed to mention something important in the description of the generalized iterative scaling algorithm. And that is that for generalized iterative scaling, this condition must hold. Namely, that the sum of all the features for any fixed x, the sum of all the features must be 1. So they have to be normalized. This may seem strange to you because we talked about these features typically being binary, having either value of 1 or 0. So if you sum over many of them, if more than 1 is greater than 1, then it'll be more than 1. Well, so what we have to do is you can think about the features as binary and design them as 0 or 1, but then you transform them in the following way. First, you define, to achieve this, call this the transformed features. First define a filler feature, which by definition takes the value of n minus the sum of the other features. I goes from 1 to n f of I of x. So this is how it's defined for every x. It just makes sure that when you add this feature in, all the sum of all the features together is n. Or some other large value that's larger than anything that would be here. And after you do that, you normalize the features to be f normalized of I equals 1 over n f of I. So you basically make them all sum to 1 by having a filler feature, adding that in, and then dividing by the sum. So it doesn't change the understanding of what's going on, but it's important if you're going to implement it. It's important to know that GIS relies on this fact. There's an alternative iterative procedure to find the parameters, which does not rely on this fact. It goes by the name of IIS, where GIS is generalized iterative scaling, IIS is improved iterative scaling. And the improved refers to computational efficiency, and sometimes it is improved, sometimes it is not. It depends on the situation. You would have fewer iterations, but in each iteration you have to invert a matrix. It depends on your situation. And there are actually a few other variants. And I don't know if I mentioned it in class. I mentioned it to some of you when we talked after class. If you remember in gradient descent, there are two ways of doing gradient descent. You can, one is called batch, and the other one is called online. You can take a step in one of the parameters of gradient descent, and then recalculate the gradient and take a step in another parameter and so forth. Or you can calculate the gradient of all the parameters and take a step in all of them together. Okay? We did not discuss this in class, but this is just general knowledge of gradient descent. The same kind of flavor exists in these iterative procedures. You can, if you remember that the model consists of 1 over z e to the negative sum of the I fi. The lambdas are the parameters. You can calculate the required change in each one of the parameters and then make a change in all of them together. That would be the batch version. Or you can calculate the required change in each one of them, one at a time, make the change, and then when you calculate the required change in the next one, it's already based on the updated model. So you can change one parameter at a time, or you can change them all together. So again, you can call it the batch version and the online version or the incremental version. Not very important, just store it somewhere, the fact that there are variations on how you derive the solutions. Yes?
How this filler is used in that function?
Yeah, so then it becomes I goes from 1 to n plus 1. That applies also to the filler. Goes from 1 to n plus 1. So you start by defining a filler feature such that this sum over all the features sums to some large number. Let's say to n. And then you just subtract, you divide by that number. So in the end, what each one of these features is instead of giving you two values, 0 or 1, it gives you two values, 0 or 1 over n. It doesn't actually matter if you take a feature function and you multiply it by a constant. It doesn't change what it does. If you multiply them all by the same constant. In fact, even if you multiply any one of them by a constant, it doesn't change what it does.
Well, because anyway, it's multiplied by another feature.
It will be multiplied by another, but the point is that you're looking, if you remember the picture of the segments that go out of the, where you're dividing it into different parts. In each one, the different feature is active. And the procedure brings out the different intersections to different levels to satisfy things. The only thing that's important is if you're inside a circle or outside it. This is what this gives you. One of them is 0, the other one is some non-zero value. It doesn't have to be 1. Okay, done with this. Short break for you to tell me about the exam. How was it? I see a variety of faces. Some good, some interested, some. Any verbal descriptions? I'm sorry?
It was fine.
Fine.
I thought it was fair.
Fair.
That's a good way to describe it.
Is there answer?
I'm sorry?
Can we find the answer to the exam?
Yeah, absolutely. So, are there any particular questions that you're not sure, that you were left confused or really eager to find out? I can describe them now. We can discuss them now. So let's very briefly. And any particular question you're interested in?
There was one Twitterling one.
Uh huh.
I wasn't really sure about that.
Okay. So the Twitter link one. So one thing I try to do in the exams is not to give you a heading to tell you which chapter the answer is in, right? But if I had a heading there, it would be the good Turing heading, okay? So it's about estimating the probability of novelty, right? And our best estimate for probability of novelty is the number of singletons over the total number. That would be the probability that the next twiddling that you see would be one that you have not seen before, right? And if there are 100 of them, then 100 times this would be your expected value. Now, if you wanted to be extremely sophisticated and to say, well, once I saw one of them, then seeing it again would not count, and if you did any of that, power to you, you still get the full, it doesn't matter. I didn't mean for it to be complicated. When somebody asked me, I said, don't worry about it, count them all as new. But if you're worried about it, power to you. Either way, but you basically have to know that it's this. I mean, what I try to do, I'm actually very proud of myself for writing an exam that not only did not require a calculator, but did not require a single calculation, even in your head. It didn't require any number. I don't think there are any numbers. I'm sorry? The one? Okay. Because in the real world, formulas are everywhere and calculators are everywhere. What I'm trying to get is for you to get the big picture so that you see a situation, you say, that corresponds to that. And that's what I can do, and that's what the advantages and disadvantages are. I find that all too often, people are able to follow the derivation, but they don't have the big picture. So I tried in the class and in the exam to focus on the big picture, on the conceptual understanding. Whether I succeeded or not, I don't know. I got one fair comment and another F comment. Fine comment. There are other F words you might want to share with me. I don't know. Okay, we will know better after we grade them. Other questions about?
I tangled myself up on the conditional entropy one.
Okay. Yeah, that was the most detailed of all of them. So the idea is that you have a vocabulary of words, and it's broken down into hard categories of parts of speech. So from an information theory point of view, the part of speech gives you strictly less information than than knowing the word. It gives you a partial amount of information, knowing the word. So the conditional entropy, this was really about understanding information theory and conditional entropy. So the conditional entropy of word I given word I minus 1 versus, say, word I and part of speech I minus 1, right? They both contain information about this word. This arguably contains more information than this one. Therefore, the conditional entropy is what's left after you know this. So what's left here is less. Now, if you were mathematically rigorous, you can say, well, what about the extreme case that the part of speech is the whole thing, and then they're the same? Power to you, that's fine. If you said this or if you said this, they're both fine, as long as you argued why. But it could not be the other way around. It could not be that you're told this and you're left with less entropy. Did I do this right? Let's see. Okay. There's a clear relationship here. Is there any other particular pair that
That the previous word is a noun. Right?
Okay, so previous word is a noun is another example where you're doing a finer division, that this one is a noun and the rest are not nouns. Right? But there is a trick there. So I told you I did not trick you, but I tricked you just a little bit. It has to do with something of this versus this. Do you remember we talked the average conditional information, average conditional entropy versus conditional entropy under a particular condition? And I emphasized in class that this is always less than or equal this. But you cannot say it about this. So if you're given that humidity is low, the entropy of temperature might actually go up or down. But if you're always given what humidity is, sometimes it's low, sometimes high, on average, it always goes down. Remember that? So I put it in there to see if you remember that. So that was a distinction between saying I know that it's a noun and saying I know it's not a noun, or just saying I know whether it's a noun or not a noun. If you know whether it's a noun or not a noun, then the entropy always goes down. Or not if it's completely independent, so it's a less than or equal. If you don't know, there's a question mark there because you don't know. You actually know something a little more than that because it's a binary condition, but I didn't ask about that. Because it's a binary condition, if the entropy didn't go down when you know it's a noun, then it must go down when you know it's not a noun, and vice versa. So one of the two cannot be positive, cannot go up. But any one of them could go up. Don't worry about it if it's confusing, but I didn't ask about that. Any other, either on this question or?
The question about the advantages and disadvantages of decision tree language models with respect to exponential models. What are the advantages of decision trees?
Training them is significantly computationally less. It's still,
Of decision trees?
yeah, so what is hard in decision trees is coming up with a lot of questions. But once you have a list of questions, calculating the mutual information of each one of them and choosing one and going forward is not that hard. Maximum entropy models are iterative models. And in the iteration, you have to normalize things. Again, it's kind of an open question. As long as you wrote things that are reasonable, make sense, arguable, I'll be very liberal. In other advantages of decision trees, at runtime, it's much faster to go down the tree and give the answer at test time than exponential models. There's always a summation over, it's a computationally more expensive process, both training and using.
As long as you have an exponential model, it's actually easy to use it, because how can it be complicated? It's just one scalar product and one exponentiation.
If it's conditional, then you have to calculate this for every. It's not very expensive to use. Relative to training it, it is much, much easier to use. So if you argue that that the use is comparable in computational, that's fine. Okay? I mean, it's still, you have to calculate that for every h, as you move along, and calculating that is summation of the entire vocabulary, and for each element in the summation, you have to do that multiplication. And you have to calculate the values of all the features. But you could argue that the feature is equivalent to attributes in decision trees, so those you have to calculate anyway.
Oh, so last time we left, you still left open the question of how to sample to calculate these Z's.
Oh, that's right. I did. Thank you. We don't have time for that. All right, let's finish the questions on the exam, and then we'll cover that briefly, and then we'll move on. Anything on the exam that you're curious to know what the answer is, or you're confused about the question?
About that HMM, if we know the whole training data,
Uh-huh.
how to train.
Right. So I hope you did not choose forward-backward, because if you know the labeling of the parts of speech, you do not need forward-backward. It is just, I mean, if you chose forward-backward, you'll get some points over a blank answer, because at least you know that you use forward-backward to train. But I was hoping that you will notice that this is a case where you have the parts of speech, you have the hidden part, and therefore the training is very straightforward relative frequency.
Just to count.
Count, yeah, Aij is count of transition from I to j divided by count of I. So in the language of that thing is the number of times you saw a noun and what fraction of that it was followed by a verb. And the same for the emission probabilities. When the labels are given, training the emission and transition probabilities is just relative frequency, maybe with some smoothing. We have to use forward-backward only when the labels are not given, the part of speech in that case.
Yeah, actually this question confused me a little because to verify, the HMM was just false tags on the hidden layer and words on the
Yes.
emission. But the expression which we were given did not have probability of emission of Wi minus 1. It only had emission of Wi and transition from pos I minus 1 to pos I.
Right, so it was probability of Wi as a function of the history was probability of Wi from part of speech I times probability of part of speech I from part of speech I minus 1. Is that right?
Yes. H was Wi minus 1, just a single.
No, H sub I?
No,
Was it written as H sub I?
Wi minus 1.
Oh, did I write here Wi minus 1?
So I expected there to be an emission of Wi minus 1 also to be in that expression.
An emission of?
Wi minus 1 from pos I minus 1.
I'm not sure I understand, but let's suppose this is the image. By the way, you could have drawn one of two things and both would have been acceptable. You could have drawn the graphical model that corresponds to this expression, which is to say you identify this as part of speech I, part of speech, I minus 1 and I, and this is word I. You can also write it, the word here too. You could do it multiple or just a fraction of this anyway would be fine. Alternatively, you could draw, say, a circle of parts of speech, any number of them, and connect them any way you want. All of them connected, and these correspond to the transitions between the parts of speech, and then each one of them has a distribution over words. You can either draw the HMM, or you can draw the graphical model that corresponds to it. Either one, as long as it shows that you know what you're talking about, is fine. Does that answer your question, or you still feel that I confused you unnecessarily? You're saying that I didn't talk about this part?
The emission of this part.
Yeah. Well, I was talking about I, presumably for every I, this is true. So this one came from, this is the I minus 1. This one came, well, this one came from pose I minus 2. But this one came from this. So, I don't know, maybe I should have said H here. I don't know.
It's fine. So the answer to your question is Wi minus 1 is in condition, so it doesn't appear on the right-hand side.
Right, it's in the conditioning part. What I try to do in grading is to answer the question, did you understand what I was trying to test whether you understood? And as long as it comes through in what you wrote, that's fine. I grade very liberally. Any other questions about the...
This question about why do we do clustering for
Yes.
particular model?
Yes, that was an easy answer, but a difficult question. Let me tell you what I mean by that. It's a very simple concept I was trying to get at, but it was clear to me that it wasn't always, from the formulation of the question, it wasn't always going to be clear to you what I'm trying to get at. And I was struggling with the framing of that question. I'm not sure I found a good solution. So clustering is about reducing variance. That's the essence of what I was trying to get at. Why would you want a cluster? In the case of what we're doing, which is predictive modeling, I mean, there are cases when you do data exploration and trying to understand the data, there are other reasons to do clustering. But in the context of everything we've studied here, the reason to do clustering is to reduce the variance of an estimate. And if you added that by doing clustering, you're increasing the bias, wonderful. But you didn't have to. If you just say to reduce, if you just wrote the words to reduce variance, got all points. Yes?
Can you say we use clustering to overcome the problem of language sparsity?
Yeah. I don't know if it's complete points, because I want to hear the word variance there. But it's a good number of them, most of them. Yeah, that's what you have to struggle with when you grade.
It's like an HMM. There is a probability of correct answer.
Yeah. Yeah.
And hidden variables.
Yeah. Because it's clear and it's true, but it's missing that little logical part of saying the reason we want to reduce sparseness is because it reduces variance. Anything else? Okay. Yes, Fatima.
This is a general question about using exponential models versus absolute models.
What are absolute models?
Models that use absolute combination of features.
I mean linear interpolation?
For example,
Okay.
in which case do we use the corrective relative models, and in which case do we use the absolute combination models?
What do you mean by correct and relative?
Like exponential models have a relative combination of features versus the absolute.
I see. So I tried with my hand waving when I introduced exponential models to say that one way of thinking about them is that they are multiplicative. They correct each other. Each feature bumps up or down your estimate by a fixed constant, either up by some percent or down by some percent, as opposed to when you do linear interpolation, you average the estimates from different sources. I can't say that one is better than the other overall, and that's almost never true in estimation. They all make their own assumptions. What can I say? I guess you have to think about these features and how do you think they affect what you know. One way you think about it is, in the exponential model, the log probability is a linear sum, is a weighted linear sum, whereas in the other alternative, it's the probability itself that's a linear sum. One way to think about it is, what is your error function? What is the measure of how good your model is. The measure we've been using, which is perplexity, which also is the same as cross entropy, which is the same as the likelihood of new data, these are all log probability measures. So you can say that your error, your loss function is a log loss. Okay? You will hear the expression log loss. That means that if you underestimate by a factor of k or overestimate by a factor of k, that counts one way. It doesn't matter if you underestimated 0.01 to be 0.001 or 0.1 to be 0.01 or 0.9 to be 0.09. In all cases, it's the same factor is what matters. So in cases where what matters is the factor, the ratio, you're effectively thinking in the space of logs. And in those cases, trying to model the log probability makes more sense to me. Because when you combine things in the probability domain, not in the log domain, you're not optimizing the right thing. I realize I'm hand-waving here. I guess the short pragmatic answer is you try both, you see which works better. Okay, that's what people would typically do. But in most, if what you're going to be tested on, what you're going to be rated on, is a log measure like perplexity, then I would argue that a exponential model, also called the log linear model, is a better one. Do you guys have a better answer?
What I think is that when you use linear interpolation, you start with some models. But when you use a log linear model, you start with features that are not complete models.
Okay. Yeah.
So does the choice depend on whether the features are independent or not? Like if we know that the features are not independent, then we would use the relative?
Both methods can handle features that are independent of it, that are not independent. Not a problem. Okay. I need to do something. Yeah, random walk. I don't want to spend too much time on it because we have very little time left for. But we had a problem left when we talked about training exponential models. We said that at some point, if you remember, we said that we need to sample from an exponential distribution. It was a way of approximating the normalizing constant. That means we need to come up with some way of sampling from P of x equal 1 over z e to the sigma lambda I f I x. This defines a distribution over all x's. Now I'm talking very broadly, language, not language, anything else. In statistical mechanics and thermodynamics, you have this distribution, and these are energy components. And they define together an energy value, kinetic energy, potential energy, chemical energy, all sorts of stuff. And then you can relate the likelihood of two states by the ratio of E to their respective energies. I don't know if you've taken physics, you know what I'm talking about. If not, just ignore it. So how do you sample from this space? When you have a multinomial over a finite space, you've all written the code to sample from a multinomial. But this is a space, a very large space of possibilities, right? Every combination of the features defines a different, distinct state. So nobody knows a good, efficient way of sampling from this state. And I don't know, they have been proven that one does not exist. I don't know if it's been proven or not, but we don't know how to do that. What we do instead is a random walk that if you follow particular algorithm for that random walk, after you walk a long enough way, in the limit, where you end up would be a random sample from this distribution. Okay? And this random walk is called a Monte Carlo Markov chain walk. Also known by the initials MCMC. So Monte Carlo corresponds to, if you cannot solve something analytically, you simulate it, you flip a coin, you follow the procedure, and then you calculate how often something happened. Markov chain corresponds to the walk is a walk where, imagine each point is one of the possible axes, and there are a gazillion of them in the space. But the system started randomly in some place, and then you're considering transitioning into this state, or this state, or this state, or this state, or this state. That's only a small number of states you're transitioning on, so you're taking a local step, and you're going to take the step proportionately to the difference in the energy level of this state and the energy level of these states. Remember, energy is this thing. So another way of saying it is you're taking it proportionally to the probability. If this is the old state, x old, and this is the new state that you're considering, you calculate P of x old, x new, and P of x old. And based on this ratio, you decide whether to take this transition or not. The important thing is that if you're only considering a manageable number of positions to transition into, you can calculate explicitly all of the probabilities. For any particular x, you can plug it in here and calculate this probability. But what you cannot do is calculate it for all the x's. There are just too many of them. I deliberately left this vague because there are several different variations. One of them called Metropolis, the other one called Gibbs. There's a Gibbs dynamic and Metropolis dynamics. I'll give you the flavor of them. Gibbs looks at all of the things that are nearby and transitions to one of them proportionately to how likely it is. So it's definitely going to transition. It looks at all of these, calculates the probabilities, normalizes them, and then jumps to one of them, such that if this one is the most likely, it is the most likely to be jumped to. Metropolis chooses one of them and decides whether to transition or to stay here based on the ratio between the two. So it's a stochastic decision. Are you going to transition or not transition? There are a variety of other ways of doing it. They all fall into the category of random walks, namely a walk that is you flip coins to decide how to go next. And the random walks have to follow this dynamics that's based on the probability that the model assigns to each one of these points. And if you do these walks, you're creating a chain, a Markov chain. And the theory says that in the limit, as the chain gets long and long and long, in the limit, the point that you get, a single point, is a proper sample from this distribution. Now, the limit thing is kind of funny because you can't wait forever. But if you do it 200 times, maybe that's good enough. So how long the chain has to be is an open question that people have studied. You know, how fast, it's called how fast do the chains mix. Depending on the form of this Markov chain, sometimes they would mix fast, sometimes they would mix not fast. As long as this is ergodic, they will always mix eventually. They move at some rate. If what I'm saying is very hazy, I'm not surprised. I'm keeping it at a very hazy level. I just wanted you to be familiar with the concepts. There has been a tremendous amount of work on how to do MCMC more efficiently. Either one long chain, and then after 200 steps, you take that sample, and then you do another 200 steps, and you take that sample, and then you do another 200 steps. The advantage of that is that the chain becomes longer and longer, so it becomes more and more close to the true distribution. The disadvantage is this correlation between the successive samples you took. If you want the samples to not be correlated, you want to start a new chain. So that's known as the debate between a long chain or lots of short chains. And then there's work on backwards chains, when you actually chain your way backwards, and forward-backward chains. There's a tremendous amount of computation because a lot of Bayesian statistics depends on being able to do this kind of MCMC sampling efficiently. Because a lot of Bayesian statistics involves integrations that cannot be done analytically, and then they basically have to be estimated. Yes?
In this figure, like this
they correspond to x's, to inputs. And for each x, there's a different set of values that the features calculate. And that will determine the sum here, which in turn will determine the probability. So if I give you a particular x, you can calculate fairly quickly what is the probability of that x.
So how do you define your graph then? I mean, so how would you define, like, if states are different inputs, how would you define how one input is connected to another input?
That's a very good question. You have a fair bit of flexibility in that choice. You can define it almost any way you want, as long as the graph that you define is ergodic, namely that you can connect from any point to any other point with non-zero, with strict positive probability, so that you could eventually mix completely. In practice, the way you define it is you make a small change to the x. So it depends on what the x's are. For example, I did this on sentences in English. So if you look at my own publications, there's a place where we do MCMC for language. I think I was the first one to apply MCMC to language, because usually it's done in physics problems. So I took a sentence that was taken from a corpus, and then I swept through, and for the first word, I just replaced it randomly with another word from the vocabulary. I actually did it Metropolis style, which means, no, Gibbs style, which means that I considered all the words in the vocabulary that could be in that position, that we could replace the first word, calculated the probability of each one of them, probability of the entire sentence based on each one of them, normalized, and jumped to one of them proportionately to its probability. And then I went to the next word and changed that, and then to the next word and changed that, so forth. So I swept through the whole sentence, one word at a time, and as I did that, you can see that the sentence changes. You know, the words change, and change, and change, and change, and then you stop after, 1,000 iterations, and you get this random sentence that is not a real language sentence, but it has the property that it was sampled from this underlying distribution. And all of that is to get one sample, and you have to repeat it a gazillion times to get a large enough sample to estimate the normalizing constant. So it's very computationally intensive. MCMC is notoriously computationally difficult. So the terms to remember here are MCMC, Metropolis Hastings. Metropolis Hastings is one form of Hastings, and Gibbs sampling. If you're interested in more details, you can start with my paper, not because it's the best one, but because it talks about language and it contains references to other textbooks. So you can go directly to textbooks. Okay, we have relatively little time left to talk about one of, I think, the most exciting topics. So maybe we'll have to continue it next time. What I want to talk about is context-free grammars. This is the first time we're getting to talk about real language. Lizzie is not here. She's our resident linguist. Anybody else here who's kind of a linguist? Okay. I'm sorry? 3 of you? Okay. Good. So this is the first time that we do something that looks vaguely like real language. Until now, we treated language as a purely statistical. Yeah, I guess we talked about parts of speech. They are real language. But the processes that we described that we pretend generate language were very non-linguistic. A Markov chain is not very linguistic. Exponential model is not very linguistic. But a context-free grammar is linguistic, right? It's not really the true language, but it's a first-order approximation. So I'm assuming that you've seen context-free grammars before. Just to remind you, you have a sentence, and the sentence maybe has a production that creates a noun phrase followed by a verb phrase followed by a noun phrase. And the noun phrase could make a determiner followed by a noun, or it could also make just a noun plural. And a verb phrase could be a verb or it could be an adverb followed by a verb. Or it could also be a verb followed by a verb by an adverb. So if you have the boy kissed girls, this is a determiner, this is a noun, this is a verb. How about passionately kissed? Girls, so then you have the adverb here, and you have the noun, the plural noun. The determiner and the noun make a noun phrase. The adjective and the verb make a verb phrase. And the noun, this is a noun phrase. And then, oh, I'm sorry. Really, the way it's usually written, you could write it like this, but the way it's usually written is the sentence is a noun phrase and a verb phrase, and the verb phrase itself contains a verb and a noun phrase, right? And the verb is a verb something, and the verb something could be adverb. So I'm not trying to be correct to English, just to give you the flavor of it. So these two connect to a verb phrase, and these two connect to a sentence. So this looks more like linguistics, right? And we know that it doesn't really capture English or other natural languages, but it does a reasonable job. It's a big step from, one word generates another word based on the last two words. So these are context-free grammars. And a probabilistic context-free grammar, also known as a stochastic context-free grammar, stochastic or probabilistic, PCFG or SCFG, is the same thing, except you have probabilities here in these transitions. And these probabilities have the property that if you take all of the transitions that start with the same non-terminal, the probabilities have to sum to 1. So this probability and this probability together have to sum to 1. So together, if the probabilities follow these rules, they describe a distribution over what? So go back to the very first lecture we had. We talked about surface part of a language and hidden part of the language. The surface part would be the list of words. The hidden part would be the parse tree. Why is it hidden? Because the same surface part could correspond to different parses. Right? So I can think of the probability, the joint distribution over the surface and the hidden, and now I want to stick to the terminology, to the notation used in the paper. By the way, there's a paper online on our website that is a very, very nice introduction to PCFGs, and I highly recommend it. Malcolm, you had a question?
Oh, I was going to try and answer the question, hopefully successfully.
So in the paper, this is called the text. I'm sorry, no, this is called the word stream, and this is called the tree. The tree is hidden, the word stream or the word sequence is the visible part, and you can write the joint distribution of the tree and the surface part. This is hidden, and this is surface. In principle, given the surface part and the hidden part, it should be fairly easy to write the full probability of getting this, starting with the start symbol S. Right? You start with the start symbol S, you look at the probability attached to the production that it creates a noun phrase followed by a verb phrase. It turns out that I only gave you one production that starts with S. So it must have be 1.0 here, so that's not important. But there could be others. And then recursively, you look at what happens here and this production. And you go back and consult your table. And you keep doing that until you get all the pre-terminals. All of them are product of these probabilities. And then you have to add to that the probability for each one of these pre-terminals generating the actual terminals. The determiner generating the, as opposed to a or an or some other word. Noun generating boy, adverb generating passionately, and so forth. So this probability can be written as, let me write it somewhere a little. The probability of the tree and the words can be written as a product of the phi's, these are the productions, times the product of the probability of individual words given the part of speech. What's the terminology they use here? Oh, they use phi for both of them. So let me just, instead of rewriting it, let me show it to you. By the way, you don't need to write down anything. The paper will be much less likely to contain errors and more likely to be correct than what I'm doing. What I'm trying to do is just give you the general idea. So let's look at
Is there a link to this paper from the
yes, of
course
course.
page?
Of course, yeah.
Well, I'm asking because for some previous notes there wasn't a link.
Oh, really?
Yeah.
Which one?
Well, I remember I had to ask.
There was a video missing.
What was missing?
A video.
A video missing?
I think it's on March 18th.
Okay, this is the guy to ask.
It's March 18th.
I think it's on March 18th.
Okay.
Oh, I think I remember that.
No, look, it comes from there. You see it? I went there. That's where I went to get it. So proof is in the pudding. Okay, so here's a nicer example. She eats pizza without hesitation. Interestingly, here's she eats pizza without anchovies. It's a very nice pair of sentences because from a context-free grammar point of view, they're the same. If you look at the sequence of pre-terminals, the parts of speech, they are noun, verb, noun, preposition, noun. But the correct tree for each one of them is different. In the case of anchovies, without anchovies modifies the pizza. So this propositional phrase is a child of this noun phrase, pizza without anchovies. What kind of pizza without anchovies? If you look at the second one, she eats pizza without hesitation, the prepositional phrase without hesitation modifies not the pizza, but the eats pizza. How does she eat it? Without hesitation. So there's an example, a very nice example of two trees that from a context-free grammar point of view could apply to either one of the two sentences. It's only us who know what hesitation versus anchovy are that we make the right matching, the right attachment without even thinking about it. But from the point of view of the context-free grammar, we have to account for both trees, the possibility of either tree being the right one under each one. So this is sort of our training data, let's say. And here are the two kind of transitions, two kind of probabilities we have. They're all with a phi letter. One is the production within the context-free grammar. So you take, one non-terminal and you produce two non-terminals. As you probably know, any context-free grammar can be converted to this normal form where all the productions are of this type, either from one non-terminal to two non-terminals or from one non-terminal to a terminal. So here's an example from each one. This is from one non-terminal to two non-terminals, and here's from one non-terminal to a terminal or a word. And it has to be a true probability, so all the transitions out of A, whether they're of this type or of this type, must sum to 1. Alpha is the general symbol for anything that comes out of a production. Now, the most important thing I want to forget about that. The most important thing I want to do for you is to create a very strong analogy between probabilistic context free grammars and HMMs. A lot of what we're going to do, the kind of problems we're going to solve, and the algorithms we're going to use are very strongly analogous. They're not the same, but they're analogous. So as I go over the problems in context free grammars, how to use them and how to train them, I'm going to try to point out what is the equivalent thing in HMMs. There's alphas, just like there's alphas here, and there's EM, just like there's EM there, and there's the equivalent of transition and emission probabilities as well. If at some point you wonder what the analogy is, stop me, and I'll tell you what the analogous part in HMM is. So can you figure out what is this analogous to, these two things? These are the two kind of probabilities in a PCFG. What do they correspond to more or less in an HMM? Transitions and emissions. So the first one, the top one, is the A, is the transition. And the second one is the emission. The difference is the topology of the dynamics is different. In an HMM, the topology is a long chain. You move at time, and which state you transition to depends on the transition probabilities. And then in parallel, you're emitting the observables, right? That's an HMM. In a PCFG, it's a tree branching process where you branch out and then at some point you produce a terminal. So the two kind of probabilities are kind of combined together. In fact, the normalization is over the two of them together. So if you're in a particular node, you can decide either to produce a final terminal, a word, or to split further into two non-terminals, and they each then are able to produce words if they want. Okay? So that's the analogy. Now,
So
yes?
in that if we rotate the HM, then it's just like the tree.
Really?
Yeah.
I don't think so. Because here I know that I'm going to produce, from every state I'm going to produce exactly one outer state and one observable. One state, one observable. Here I can produce many, many hidden states. And then each one of them, this is recursive. This is a recursive structure. This is a linear structure.
If the linear structure can be contained in the recursive structure.
Yes, but in a degenerate way, that you always have to make a certain decision. Right? Suppose you rotate it down like this. Is that what you mean? These produce words? Or that, you produce one state and one word. And then, and then another state and another word. And another state and another word. So, yeah, so you can say that this is a special case of a PCFG. It's a very degenerate special case where you're always producing one. But the fact that it's linear is what makes it simpler to develop the EM algorithm for it. Okay, the next thing you do, next question you ask in EM is, suppose you knew the full model, how would you evaluate the probability of some observable sequence, right? We'll do the same thing here. We call it the evaluation problem. I'm sure you're very familiar with it now because we spent countless nights implementing it. Eval problem. Given the model, the PCFG, which means you're given all of these productions, the productions and the probabilities, and given an observable sequence, namely the sentence W1, Wn, calculate the probability of the observed sequence given the model. I guess I'll call the model lambda just like I do in HMM, and the observer and the sorry, I called it W and no, no tree. That's it, given nothing. Calculate the probability of the sequence given the model, right? That's the equivalent of the evaluation problem in HMM. You could write this as sum of P of word and T given the model, sum over T. Yes?
But here we have a constraint that you have to reach the starting state. Unlike HMM, so you can estimate the model, but we have a constraint that whatever model
You have to start from S.
on the first stage.
Right. It's implied that this came from S. That starting with the symbol S, you ended up with this. That's the implication. You always start with the symbol S. Calculating this for any particular tree is easy. You just go to the tree, and as I mentioned, you follow all these transitions and you multiply together all the probabilities that are above all the transitions. So this is easy. Easy. Multiply together the appropriate thetas. Since you're given the tree, you know what the thetas are that were used, which transitions were used, where, and you just multiply all of them. Doesn't even matter in what order. Where's the problem? The number of trees. Very similar to what we did in HMMs when we summed over all hidden state sequences, remember? There we had the sum of A times B times A times B times A times B, and we said this is easy to do, but you have to do it an exponential number of times. When the number of trees, the possible trees, typically grows exponentially with the length of a sentence. So just like we came up with the dynamic programming algorithm for HMMs, there is a dynamic programming algorithm for calculating this in polynomial time. And you may have seen this algorithm if you took algorithms for NLP with Alon. How many of you took it? So did you see CYK? Okay. So it's explained in this paper as well, but I'll show it to you anyway, just briefly. Here's what you do. You start with this upper triangular table, and you write the words of the sentence next to it. And then you fill this table, and you fill it in this order. You first fill this, and then you 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 fill that. And what each one of these correspond to is, in this square, pull it up a little bit, say this square goes from here, from word number 3 to word number 4. So this square is responsible for all the possible derivations of, complete derivations of the fragment of the sentence from word 3 to word 4. And all the possible non-terminals that could be sitting at that point. So this diagonal is responsible, each unit is responsible only for the word. This is from word 1 to word 1, this is from word 2 to word 2, all the way to word 5, from word 5 to word 5. So it's looking at just one word, a fragment of length 1, and asking what could be effectively the part of speech, or the non-terminal for that word. And then you recursively build what could be sitting here. So what could sit here, this goes from 2 to 4, is all the different derivations that could happen that started from a single non-terminal and ended up with the words in position 2, 3, and 4. And the recursion comes from each diagonal uses recursively the diagonal below it. And when you get to the top, there would be an S here, and it would account for the whole thing. Okay? I don't expect, if you've never seen it before, I don't expect you'll understand all the details, but we don't have time to look at all the details. The paper does describe them in detail. Here's what it looks like after the first diagonal is filled in. If one of the words were polysemous, or poly, whatever you call it, if the word could be both a noun and a verb, then inside the square, there would be more than one non-terminal. It would be n, comma, v. So it could be a noun or a verb. And what you're not seeing here, but is written here, is you don't store only the non-terminal that is a possible parent of this particular substring, but you also store the probability that this parent would result in all the children underneath it. And that's also derived recursively. So again, the paper describes the detail. And here is an example of a position that could be either a noun or a noun phrase. So this position corresponds to the fragment pizza without anchovies, okay, from position 3 to position 5. And it could be, how could it be a noun? I don't know. Does anybody know why it could be a noun?
I think that's considered pizza.
I'm sorry?
Aren't they using N as an NP?
Yeah, N is a noun phrase, and NP is a noun followed by preposition. Yeah, probably. Okay, so either it's pizza without anchovies is a noun phrase, that's the N, or it's a noun followed by a preposition that still waits to be attached. I'm not sure. You'll need to read it to see the detail. Okay, the important thing from an algorithmic point of view is that there could be multiple subparses of that fragment of 3 words. And they're all going to be written there, each with its own probability of generating it.
Total probability.
That's total probability of starting from that non-terminal and ending with the list of words underneath it.
So it could have 5 derivations and they all added up to...
Yes, and that's exactly what the dynamic programming does for you. It calculates all the different ways in which you can combine children underneath you, which themselves already calculated all different ways that they themselves could be combined. So you're avoiding the combinatorics.
You're enforcing that you have a binary branching tree.
Yes, yes. And the way I did it is by converting my context-free grammar into the normal form, where every transition is either into a terminal or into 2 non-terminals. That's Chomsky normal form, I think. So this is how we solve this problem, the evaluation problem. Just like we have Viterbi in HMM, which is the decoding problem, we can also do it here. We can ask which tree is the most likely tree given the observation. So this, if you want to produce your top parse, you would ask which is the most likely tree. And the algorithm would be very similar to this algorithm, but instead of summation over all possible parses, you will take the higher likelihood one. So there's a complete analogy. The difference is in the graph structure. Is it right to left? Left to right, depending what country you come from. Or is it a tree branching? So all this was based on being given the model. The 2 relatively easy problems, the evaluation problem and the decoding problem. Now comes the hard problem, which is the training problem. In the HMM, there were 2 parts. There's the structure and there's the parameters. The structures is how many states you have and how they're connected to one another, also called the topology. The parameters are the values of the emission and transition probability matrices, right? Here we have the same thing. The structure is the list of transitions in the context-free grammar. And the parameters are the numbers that sit on the arrows. So we're not going to do structure learning. That is very hard. Just imagine the number of possible grammars. Each set of productions, of derivations, is a different grammar. The number of possible grammars is exponentially large, doubly exponentially large. It's very, very hard to learn grammars, although people have tried. We're going to assume that somebody gave us the CFG, and we have to add the P in front of it. We have to probabilize it. So a linguist gave us a list of productions that they believe describe a particular natural language, and we have to decide on the right probabilities to put on it based on a large collection of sentences. So now we have to split based on whether these sentences have been annotated or not, just like in HMM. If the sentences have been annotated, namely a human looked at each sentence and built a tree for it, that becomes very easy, just like in the question I had in your exam. If you have the hidden part of your training data, then training the parameters is just relative frequencies. Right? Let me find the relevant. In HMM, it would be the number of times you see a transition from I to J divided by the number of times you were in I. In context-free grammars, it would be the number of times you see transition, say, from noun to determiner noun divided by the number of times you see a noun. So how many times when you saw a noun in your parses, it's split into a determiner and a noun. It's just relative frequency. And similarly, the number of times you saw noun that went into boy divided by the same denominator, kind of time you saw noun. So what is called transition and emission in HMMs is actually fused together into one set of probability distribution. So if you have a large set of parsed sentences with the intermediate values annotated with their part of speech, or whether it's not a part of speech, what is it called? Preterminals? What do linguists call the labels? Noun phrase, verb phrase? Non-terminals? Okay. Non-terminals. As long as the non-terminals are present and the tree is fully specified, you just count. And of course, if some of them are very low count, you might want to smooth it, but it's basically a very simple problem. The problem becomes more difficult when the corpus is not parsed, is not annotated. Just like in an HMMs, it becomes difficult when you don't have access to the state sequence, only to the observables. And again, we're going to use EM. We're going to do it iteratively, exactly the same story. So in HMM, it's called the forward-backward algorithm because you do the forward pass to calculate the alphas and the backward pass to calculate the betas, and then you use both of them to calculate xi. Things it's xi. I always have a hard time with that. And you use that to re-estimate the emission and transition. We're going to do the same logical step here, except it's not going to be a forward and backward sweep. It's because it's a tree. In a chain, you can do forward and backward. In a tree, you can't do forward and backward. What you have to do is recursion into a fragment. So here's the word 1, word n. And we're going to look at the sort of alpha value of some fragment here from j to k. And we're going to base it on recursion into smaller fragments, and also recursion based on the outer parts, here and here. So this is going to be called the alpha part, and this is going to be together be called the beta parts. And if you remember in HMM, I don't expect you to follow details, just to get the picture. In HMMs, we could piece together an alpha value and a beta value that together account for the entire sentence. Remember we had that picture. State I, state j, time t, times t plus 1. Alpha accounted for this part, alpha t of I. Beta accounted from this part on beta t plus 1 of j, something like that. We pieced together an alpha value and a beta value, and they accounted for the whole chain. Here, we're going to piece together an alpha value and two beta values to account for the whole tree. which is why it's called the inside-outside algorithm. Alpha is the inside, beta is the outside. So let's look at what it looks like here. Let's first define. All right. Here's a definition of alpha. We'll follow the slide, and I'll draw it. I'll draw it on the board. Word 1, word 2, word I, continue, word J, continue, word N. I'm going to try to account for this part. This is going to be alpha I comma J of non-terminal A. One difference between the alphas and HMMs and the alphas in the inside-outside algorithm, which is the algorithm discussed here, is that in HMMs, alpha is a two-dimensional table. One dimension is time, the place on the chain, and the other one is which state you're in. And the implication is that alpha is from the beginning. So when I give you a time t, alpha of t, it means from time 0 to time t. Here, I have to give you specifically from time I to time j. The I and the j here are not indices over states. They're actually indices over time, or over the progression of words in the sentence. So alpha accounts for what happened from word I to word j, and for the non-terminal that sits at the head of this tree being A. So A is a particular non-terminal. And the definition of alpha ij of A is the probability under the current model, the current set of parameters, that a non-terminal A would result via any number of productions. This is the star. The star means any number of productions in this particular sequence of words, W1 through Wj. So for example, it could be that a noun phrase will, under various productions, end up being the big red apple, part of a long sentence. The boy ate the big red apple and blah, blah, blah. So the big red apple came from some noun phrase, and it's the probability that starting from this, you went through various transitions, all of them accounted for by parameters of the model, and ended up with this. Beta is the complement of that. Beta ij of A, just like you have alpha ij of A, beta ij of A is the probability that starting with the initial sentence symbol, starting here, you've generated somehow these words from W1 through Wi minus 1, followed by A, followed by the words from Wj plus 1 to the end. So here it is. It's the probability of S becoming the sequence of words followed by A, followed by this sequence of words. So if you multiply together alpha ij of A and beta ij of A, you get a probability of generating the entire sentence and insisting that the words from I to J are sitting together under a heading of A. The alphas and betas in HMM were calculated recursively, but it was a very simple recursion. It was sort of recursion in time. You fill the t plus 1 column based on the t column. Remember that? The alphas and betas here are also filled by recursion, but it's a more complicated recursion. Alpha is defined in terms of other alphas that are smaller. Beta is defined in terms of both alphas and betas. Let me show you the recursion, and I'll show you the picture. It will make more sense with the picture. Here is a picture of how we do recursion of A, of alpha. So we want to calculate the probability that A gives rise to all the words from I to J, from word I to word J. Well, we have to sum over all different ways in which this could happen. And how could it happen? A could use some kind of production to become B and C. And we have to allow for all different ways in which it could happen, all different values of B and all different values of C. And for each one of them, if it became B, we're going to recursively ask what is the alpha value of starting from B and accounting from the words from I to some K, and then starting from C and counting from the words from K plus 1 to J. And of course, the exact value of K could be anywhere between I and J. So we need to think of all the different ways of breaking the range from I to J into two parts, and all the different ways in which A could break into B and C, whatever B could be, whatever C could be, and then each B what it would be and each C what it would be. Okay? We can do that. To do that, we construct the recursive relationship, and let me find it for you here. Here is the recursive relationship. Alpha ij of A is a sum of all different B's and C's, and a sum of all different ways of breaking I and J in the middle with a K. And then for each one of them, we have to take into account the probability that A becomes B and C, and of course, if there is no such production, it's 0. And if there is such a production, we take that probability and then we multiply it by the probability of B accounting for the words from I to K, and C accounting from the words from K plus 1 to J. So the recursion here is on the length of the subsegment that the alpha correspond to. The alpha from I to J is defined recursively in terms of other alphas on smaller regions, regions of smaller distance. From I to K and from K plus 1 to J is smaller distance than from I to J. So the recursion is, in recursion you have to make sure it bottoms up. When does it bottom up? When you're down to one word. So it's II or JJ. So the way you effectively do this, you could mathematically write it as a recursion. In practice, you start by calculating the alpha values of fragments of a single word. Alpha II of A, alpha II of B, alpha II of C. For every pair of II, 1, 1, 2, 2, 3, 3, 4, 4, 5, 5, all the way to NN, and for every possible non-terminal, A, B, C, D, E. And when you finish that, you move to the next level up, where you consider fragments of length 2. It's just like in the CYK algorithm. And you calculate alpha of 1 to 2 of A, alpha 1 to 2 of B, alpha 1 to 2 of C, and then you move to alpha 2 to 3 of A, alpha 2 to 3 of B, alpha 2 to 3 of C, and so forth. When you're done with that, you move to all fragments of length 3, all fragments of length 4, and all the way. So that's how you recursively calculate all the alphas. What about the betas? Here's a picture of beta. The shaded area, I need to let you go. Let's just finish this recursion. The shaded area, I don't know if you can see what's shaded. This part and this part. The beta that applies at B here says, beta that applies at A. Beta applies at A from here to here, says I want to account for everything that happened outside of A. So what I do is I go up and I say, where did A come from? There must have been some other non-terminal, call it B, the parent of A. And B had a production that resulted in C and A. It could have also been in the opposite direction, that A was in the left side. So I actually have to sum over these two cases, where A was a right child and when A was a left child. Let's assume that A was a right child here. I calculate everything here by calculating the beta value from B, which accounts for these parts, and then calculate the alpha value of this part. So I play with these triangles to get exactly the part I want. So the recursion that comes out of it is beta is expressed in terms of other betas and other alphas. The important thing is that the other betas are bigger. Are they bigger or are they smaller? Yeah, they're bigger. I want this beta, and I express it in terms of this beta. So there is a directionality to the beta recursion as well. So there's a bottom up. So now let's pop up a level and say what the whole algorithm is. You start with some random values of the transition parameters, initialization. You use those as your tentative iteration L parameter values. You calculate the alpha and beta tables. They're not 2D tables, they're kind of 3D tables. They have I, J, and index over non-terminals. After you calculate the alpha and beta tables, you can use those to calculate the expected value of every transition. Remember the Z's in HMMs? Since we don't know the transitions, we can't count them, but we can count their expected values. And you pretend that these expected values are fractions, and you do a maximum likelihood or relative frequency estimation of those fractions. And this gives you new values of the parameters. And then you repeat the process. Standard EM. One caveat, this EM is notorious for getting stuck in local minima or local maximum. So even it's a big problem in HMM, it's an even bigger problem in PCFGs. So it's not really a great solution. We don't really know you can run it multiple times, starting in many different places, but you don't really know if there's a better set of parameters that you haven't found yet. So you're much better off investing in annotating the data and then doing supervised learning. This you can think of as unsupervised training, without the tags, without the labels. You're better off investing because you'll do better. All right, we'll go back and review this and can ask questions next time.